Okay, so in example 5, we're going to look at the joint density function, the same one that we had in example 4. Let me go ahead and remind you what that looked like. There we had this graph, and we're looking at the entire positive quarter plane there. So there's y1, and there's y2, and everything's going from 0 to infinity. But we want to find the probability that y1 plus y2 will be less than or equal to 2. So let me draw the line y1 plus y2 equals 2. There it is. It's a diagonal line. It's got slope -1. So that's the line y1 plus y2. y1 plus y2 is equal to 2. It's just x plus y equals 2, and you could solve that out, and you could do a little algebra to find that. It does have intercept 2 on each axis. So I want to be less than or equal to 2, which means I need to look at the region underneath that line, and I want to describe that region and then do a double integral in order to find the probability of landing in that region. So the first thing I'm going to do is try to describe that region. And it doesn't really matter which variable you list first here, but I listed y1 first, so I can use constants for y1. I'm going to go from 0 to 2. And then I listed y2, but I can't use constants for that because otherwise I'd get a rectangle. So y2 goes from 0 to, if you solve that line out, you get y1 plus y2 equals 2. If you solve for y2, you get y2 is equal to 2 minus y1. And so I'm going to use that as my upper bound. That's going to make for some nasty integration, but there's no way around it. We just have to go through it. So my probability is going to be the double integral on that region, but I've already set up the limits here. So actually, I've done the hard part. The rest of it is just sort of tedious integration. y1 equals 0 to y1 equals 2, and y2 equals 0 to y2 is equal to 2 minus y1. And now I have that same density function, e to the negative y1 plus y2. And now let's see, I have dy2 and then dy1. And remember the old trick that we used back in example 4, it works again, is to write that density function as e to the negative y1 times e to the negative y2. The utility of that is that we're integrating y2 first. That means e to the negative y1 is a constant, and I can pull it out of the integral. So I'm going to pull that out of the first integral, of the inside integral. E to the negative y1 just sits there on the outside, and I have the integral of e to the negative y2 dy2, and then later on I'll do the integral with respect to y1. So e to the negative y1. Now the integral of e to the negative y2 is negative e to the negative y2. And I need to evaluate this from y2 equals 0 to y2 is equal to 2 minus y1. And there's still a dy1 here. Now this is a little bit nasty. I got negative e to the negative y2. If y2 is 2 minus y1, negative y2 will be y1 minus 2. Minus negative e to the negative 0, so minus negative 1. And so I'll get positive 1 minus e to the y1 minus 2 at the next step. Now I'm going to bring in this e to the negative y1 from over on the left, and I think that's going to be useful because I'm going to go ahead and multiply that through. I think it'll simplify things a bit. I get e to the negative y1 minus e to the negative y1 plus y1 minus 2. So e to the negative 2. That went a little sideways there. E to the negative 2. So that's not too bad. And what am I supposed to do with this? I'm supposed to integrate it with respect to y1. dy1. Let me go ahead and keep going on the next column here. The integral of e to the negative y1, do a little substitution. It's negative e to the negative y1. E to the negative 2 is just a constant, so it's negative e to the negative 2 times y1. And this whole expression is supposed to be evaluated from, where were my limits? Oh, right there at the beginning. y1 equals 0 to y1 equals 2. So I'll plug in y1 equals 2. I'll get negative e to the negative 2 minus e to the negative 2 times 2. Now if I plug in y1 equals 0, I get minus, plus 1, because the two negatives cancel. I'm subtracting a negative. And then plus 0, because we've got y1 equals 0 in the last term there. This simplifies a bit. I've got 1 minus e to the negative 2 minus 2 e to the negative 2's. So 1 minus 3 e to the negative 2. That's as good as it's going to get. I did plug that into a calculator to get a decimal approximation, and my calculator told me that that was 0.594. Again, it's between 0 and 1, so that's reassuring. Every probability answer should be between 0 and 1. And so what I get there, if I wanted to make that into a percent, that's 59.4%. So that's my probability of landing in that sort of triangular region in the corner. The probability that y1 plus y2 is less than or equal to 2. So that's the probability that I've been asked to compute there. So let's recap that. First of all, I graphed the region, the whole region, which is all the positive quarter plane here. Let me see if I can draw that without making things too messy on the graph. So that's kind of the whole region, but that's not the region we're interested in. We're interested in the region where y1 plus y2 is less than or equal to 2. So I had to graph that part of the region. So that's what this diagonal line is. It's the line y1 plus y2 is equal to 2. And then we wanted all the region less than that. So that's why I colored in this blue triangular region here. And then I was trying to describe that region in terms of variables. I can use constants for the first one. y1 goes from 0 to 2, but I can't say y2 goes from 0 to 2, otherwise I'd have a square. I don't want a square, I need a triangle. So I said y2 was less than 2 minus y1, and that came from solving out the equation of the line in terms of y2. That's how I got that. Once I had that description, that was sort of the hardest part of the problem. Then I just dropped those in as my limits for the integral, and I dropped my density function in. At this point, you could drop the entire thing into a calculator if your calculator will do multivariable integrals. Otherwise, you could throw it into some kind of computer algebra system or an online integration system. But I'm trying to be honest with you. I'm trying to do it by hand. So I factored e to the negative y1 plus y2 as e to the negative y1, e to the negative y2. The important part about that is that in this first integral, this inner integral, we're integrating with respect to y2, which means we can treat y1 as a constant. That's why I pulled the e to the negative y1 all the way out of the integral, which gives me a nicer integral, e to the negative y2 on the inside. That integrates to negative e to the y2, and then I plugged in my bounds here to get something a little messy. I multiplied the e to the negative y1 back through, and it simplified a bit. And then I integrated that. E to the negative y1 integrates to negative e to the negative y1. E to the negative 2 is a constant, so that gets, when you integrate that, it's e to the negative 2 times y1. And then I plugged in the bounds y1 equals 2. All the way through, and y1 equals 0. Simplified it down a little bit to get this slightly mysterious number, 1 minus 3 e to the negative 2. But when I converted that into a decimal, I got something that was between 0 and 1, so that's a little reassuring when you're doing a probability problem. If it had not been between 0 or 1, I would have known that I was wrong. and then I converted that into a percentage. Any one of those forms, if you gave it to me in my probability class, I would be happy. So you don't have to convert it into a percentage, but if you like to know what it is as a percentage, there it is. So that wraps up this lecture on bivariate density and distribution functions. This is part of the chapter on multivariate probability density and distributions. We're going to move on to marginal and conditional probability in our next video. This is all part of the larger lecture series on probability here on Educator.com. I am your host, Will Murray, and thanks very much for watching today. Bye-bye now.